Hi all, a very warm welcome to the course for Probability for Computer Science. As we know in IIT Kanpur, this is known as CS203. This is the first introductory lecture. Today, we are not going to talk about anything technical, but just give you an introduction about the course. That means what will be covered and why is it important for you. All the information about the course will be present on the course web page. These videos are just for the help. I think a much better resource would be the course notes. So ideal thing would be that you look at the course notes and these videos simultaneously. All this can be found on the course web page. I will give the link at the accompanied YouTube information. If not, you can just search my name and probability course IIT Kanpur on Google, and you should be able to find the course web page. This is the course web page for course CS203. There you will find demos also, notes also, which are important. Starting with the course, why do we need to learn probability? Now, I would say that for most of the computer science people, this might seem like a mute question. Obviously, probability is very, very important. There are so many areas. You have statistics, you have physics, you have quantum mechanics, very, very important fields of science where probability forms the backbone of these fundamental theories. And now, with the advent of AI machine learning, you see that probability is everywhere. Actually, in almost all areas of computer science, you need some background in probability. And if this does not motivate you, there is always gambling. So if you want to make quick money, I'm not supporting that, but yeah, that definitely requires probability. And historically, probability started because people wanted to gamble. So they developed the theory of probability to smartly gamble. Anyway, we will learn it because of similar reasons. I'm almost sure that you were introduced to probability in high school, right? And you have calculated probabilities of events like when you toss a coin, can you get two heads in succession? What is the probability? You throw a dice, and what is the probability that a prime number shows up? Simple questions like that. So your question might be, oh, I already know the probability. Why do I need to learn more? The main objective of this course is to develop a solid framework to tackle all these questions. And not just these questions, but talk about many more advanced questions. What kind of questions are we interested in? Let's take a look. We will start slow. First question could be, you roll two dices. What is the probability that the outcomes you observe on the two dices are co-prime to each other? Again, since you have taken a course in probability, this is not a very difficult part. You will see that there are total 36 possible outcomes, 6 times 6, and then a simple counting will give you number of favorable outcomes. That means the outcomes where both the things are co-prime. I will not give you the answer. You should probably do this exercise and make sure that you can get this answer. This was not very difficult. So let's talk about this question. Suppose you have a circle and let's take an equilateral triangle inside this circle. Pardon my drawing. We will assume that ABC is an equilateral triangle. So all the sides are equal, angles are 60 degrees. Now you draw a random chord. So you pick a random chord inside the circle, and the question is, what is the probability that the length of the chord, the one which you have picked, is more than the side of the triangle, right? So you have length of AB, BC, CA, all of them are equal. So you want the probability when you pick a random chord that the length of the chord is more than side of the triangle. You might want to give it a try. I will just show you some of the approaches. Now the first approach could be that you pick two endpoints. Without loss of generality, fix one at A. And now the other point of this chord can vary from anywhere up to here. And you realize that the length is more only if the endpoint lies between B and C. So this tells you that the probability is 1 by 3. Seems this question was not hard. But let's take another approach. We know that the chord on a circle is defined by its center. Where should the center lie so that the chord has length more than the side AB? And you will see that this happens only if the center lies in this smaller circle. I will not give you the details, but you can check that the radius of this circle is going to be the half the radius of this bigger circle, and that means the probability will become 1 by 4. So when the center lies in this circle, then the chord is bigger, otherwise smaller. What happened here? The answer came out to be different. We can also define the chord by its distance from the center. Now, by a similar argument as in the previous case, the distance of the center should be less than r by 2. So the distance varies from 1 to r. If the distance is less than r by 2, then our chord is bigger. So that will give you a probability of half. So we got 3 different answers. Which one is correct? This might be a question in your mind, and I will let this be a question in your mind. We take more interesting questions. Suppose you have a horizontal plane, infinite plane, and you have lines drawn on it at a distance of 1 centimeter each. So it's an infinite plane, there are infinite lines, all parallel lines have a distance of 1 centimeter. Now you take a needle of length, for easy things, let's say 1 centimeter, and you drop that needle on this plane. Question is, what is the expected number of intersections of the needle from these lines? So you drop this needle arbitrarily, and we are interested in finding out the expected number of intersections with these parallel lines when the needle is dropped. All these were mathematical problems, so let's take something more related to real life. Let's go to hospitals. I know you don't want to go to the hospital, so let's take an example from the hospital. Suppose there is a diagnostic test for cancer. That means it tells people whether they have some kind of cancer or not. It's 95% accurate according to the website of that test. What does it mean it is 95% accurate? If a person has cancer, then it tells you that yes, that person has cancer with more than 95% probability, and it gives you an answer no with less than 5%. So it tells you correctly with 95% probability. If person does not have cancer, then It should answer no, and it answers no with probability more than 95%, and it answers yes with less than 5%. So, for any kind of patient, whether they have cancer or not cancer, the answer is correct with probability more than 95%. Seems like a good test. So, I need someone to test for it. So, let's say, okay, I go for a test, and the test turns out to be positive. You already know this statistics about the test. Now, I got tested, and the test turns out to be positive. Question is, what is the probability, obviously, that I have cancer? You might say 95%. Actually, many qualified medical professionals also give the answer as 95%, but that is incorrect. I will let you think about this question and take you to more questions about the medical field. So, there was a hospital in England which had malaria and dengue patients, and when people were tested, it was found out in that hospital that fraction of people with malaria, so out of total number of people in the hospital, people who had malaria, was actually much more than fraction of people having malaria and dengue in dengue patients. So, in some sense, one quantity talks about people having malaria. This probability talks about probability of people having malaria when they already have dengue. And it seems that dengue, if you have dengue, then the probability of having malaria is less. What could be the reason? You would say this has nothing to do with probability. Probably once you have the dengue bacteria or whatever, the malaria does not come out or something. Turns out this is a probability question. How? For that, you have to learn more in this course. If this is not good enough for you, let's talk about one more survey. A survey was done in small, not actually small, but lot of localities in a country. They calculated the fraction of people having diabetes in total population. So they wanted to figure out how healthy is the population. So they looked at different cities, towns, villages, and found out the fraction of people who have diabetes. What were the results? They found that the five best villages. What do I mean? Five best villages? They have the smallest fraction of diabetes patient. These, all these were small villages. So I should say the five best localities which were the healthiest, the fraction of diabetes patient there was smallest. Those were all small villages. What could be the reason? And most of us would think that must be because there is a lot of fresh air in the villages, the lifestyle is active, seems reasonable, but it also turned out that the five worst villages, or I should say, five worst localities, that means the fraction of diabetes patients was the biggest in these localities. These were also again small villages. If this was given to you independently, you might have blamed it on worse healthcare awareness issues. But now, keeping both these statistics in mind, it seems that probability can explain it. How? For that, again, we have to worry about the course. All these questions had some kind of probability framework. Let me tell you questions where no probability is mentioned. For example, the question about antichains. What is an antichain? You are given a set of n elements, and an antichain is a set of subsets such that no two are contained in each other. That means there does not exist U and V such that either U contains V or V contains V. And now I ask, how many antichains are there? And these kind of questions actually can be answered using probability. The question has nothing to do with probability, and still you can answer it using probability. Another question like that, let's pick a set of n integers, and I would say non-zero integers. You will see why non-zero is important. And what we can show is that however you take B, there always exists a subset S of B, which is pretty big. It has size more than n by 3, so it is at least 1 by 3rd size of B, and still S is sum free. S is sum free means there does not exist S and T in S such that their sum is also in the set S. You can try to create sum free sets and you will see that creating it for arbitrary sets is very, very hard. So it is very, very surprising that in any set of size n, you can always create a sum free set. But again, more importantly, there's all these statements can be proved using probability. A lot of these questions which are very, very interesting, a lot of the questions have nothing to do with probability tools can be used. And this is what we are going to learn. And for that, a basic probability framework is not enough. We need a solid framework, concrete framework, through which we can develop our theory of probability. So we will install a framework first, and then we will see how clearly we can answer all the questions which we have seen just now. So we need clearer approach as compared to what you have seen in the high school. And that's what we will derive. This will help us in countering 50-50-90 rule. You know what a 50-50-90 rule is? It's a quotation which says that whenever you have 50-50 chance of getting something right, so with half the probability you can get something right, you get it wrong 90% of the time. This is a quote by Andy Rooney, and hopefully after this course you will be better at avoiding these pitfalls. I will end this lecture today here. In the next lecture we will start making our framework for